Well, when the bell goes, wait those notes. Because now I am streaming and I can go get the demo. Well, make the demo.
It's just a step. Yeah, so this. That is fine, just to organize it, organize it when I have time and I have no time. I'm excited to go to university. I keep getting first of, wow, I get to go to new things. And then I keep getting first of, oh my god, those new things are really hard. I'm like, those new things aren't gonna be hard. Like, I can do that. I just pass it. Like, in uni. At the end of the world, if I go. Oh, I have to go to another program, so it is for me, but because if I don't, I have to keep an 80 average. Oh, that's not bad. For university it is. Because remember, what is season before? Like calculating my grade is like it's like divide in half at 20. I don't know. Yeah, like work wise, no, but it's because like lifestyle wise, it'll even out to be as well. Another friend that went next to her here, they're like, oh yeah, like it's like easy, like really like it's super hard, but if you come up early, yeah, like just these people don't want to like do homework, like how said like I had like way more free time. Students see a 10-point drop in their grade regularly when going to university, so that, and that's in McLean's. This one was using along with your like half your grade now and then half that. Oh, that's great. If I have a 90 average, half of that is 45, and this gives me a 65. So get into that stuff. Oh, okay, but so it's also a lot better than that. No, I know, but I'm just saying. But just because she says that doesn't. I know it's not necessarily true. Saying like 80 isn't super achievable. That's why people don't get into that school. I need to have an 80. I need to do well in the interviews and everything else. I need to have more experience and I need to have a little bit of increase. You have to have higher than me. It's just really, it's not, it's one of the harder programs to get into, and I know like, oh, not like other, it's not like one of the specific hardest, because like, one of the hardest is like commerce, because like they're easier, but like program in general is one of the hardest, not easy, because there's a lot of functions.
That's really gonna be the coach today.
Oh yeah. Hello, everybody has notes down. Buffers work with only as many moles as you have. Only works for small amounts of acid and
Okay,
bases.
we're supposed to have those down?
Oh, and go, go, go. I told the people that were here.
I was here on time.
I just did that before I went and got the demo. Go down now. We did it last day. Works with only in that we talked about it. Buffers only work with as many moles as you have, and only works for small amounts of acids and base. If you run out of moles in the equilibrium, obviously you're not going to have enough.
Okay.
Anyone else still ready? You should ready. Go. NA? Almost done? Good. No, don't take a picture. Write it down. There's no learning if you take a picture. You ignore a picture later.
You're gonna move it so you can bring it. from
No,
the
no,
side.
keep writing. I'm waiting for you and glaring.
Doesn't that also not help with learning because then you're pressured to just copy it down without thinking about it?
If you join the Army Corps of Engineers, you will do one of your exams in a live round fire.
What?
Stress is always good in a learning environment.
Oh, wait, what
No,
are
but
they
isn't
trying
that
to
just to
do?
prepare for like battle, not?
Medieval research shows,
Yeah.
Medieval.
like literally medieval research shows, when they were training knights, they found out that when they made a mistake, if they like threw them in cold water afterwards, they learned faster.
So if you punish those.
So they would have them, charge at this little tiny target with their lance, and if they missed it and hit in the wrong spot, a big weight would swing around and knock them over off their horse into a pond.
That would hurt so much.
Smart people.
Oh.
Why does it only work for small amounts of acid and base though?
Pardon?
Why does it only work with small amounts of acid and base?
If you have, this is from last day, well, let's do the next page for equilibrium. Let's say you've made this equilibrium in a different color. We've made this equilibrium, and we have lots of these on both sides because we've added sodium acetate and this. But when we say lots, let's say we mean 0.1 molar. Which is lots compared to the, times 10 to the minus 5 of H plus that we have. If I add hydrochloric acid to this, what goes up and down and which side does it shift?
H plus.
H plus goes up, and which way does it shift? Left. So it goes up, it shifts left. If it goes up and shifts left, and I add 0.2 moles of HCl, what will happen?
It all goes to the
0.1 moles will go to the left, and then what will happen? You have 0.1 moles of excess that's now just going to make the solution acidic. The buffer no longer works. So it only works for as many moles as you have. So buffers are limited by how much of the acid bases you can put in. This, yeah?
So just having the conjugate acid and conjugate base, that makes it a
That makes a buffer. As long as you have enough of both. If you only have one of them, like you just added acetic acid, just a solution of vinegar, then it's only going to work against base. If you only have sodium acetate, it's only going to work because it only shifts one way. We're going to use red for acid. We'll use blue for base. In this equilibrium system, and this is just reintroducing Le Chatelier's principle, we're going along, and then at time t1, I add acid. What happens in the equilibrium?
It'll go up
Spikes up.
and then goes back to equilibrium.
Yeah, it goes back. Does it go all the way back to the original?
No, it's
No.
higher, but it's like.
Yeah,
goes
but
down.
not much higher. Let's, want that. Let's put a dotted line in here. Just so we can shift. Similarly, if this is concentration of HPL plus and I add NaOH, what does it do? Spikes down because we get rid of some. And so a buffer is just using Le Chatelier's principle. to make sure that the concentrations stay about where they should be. Whatever you do, nature tries to undo, so we take advantage of that undo process. Like I said last day, if your acid in your blood changes slightly, hemoglobin is bound within 0.02 of a pH. 7.4 releases oxygen, and 7.38 absorbs it. If it's at your lungs, it's less acidic, and so it binds the hemoglobin binds oxygen. And if it's at your tissues, it's more acidic, 7.38, and so now it releases oxygen and binds CO2 and hydrogen. How many of you are in anatomy and physiology? If I say reduced hemoglobin, oxyhemoglobin, and deoxyhemoglobin, and carbaminohemoglobin, does that all make sense?
No.
Some of that? Because you have hemoglobin, which at 7.40 will react with oxygen to make oxyhemoglobin. That's deoxyhemoglobin. Hemoglobin at pH 7.38, hemoglobin will bind with CO2. Deoxyhemoglobin will bind with CO2 to make carbaminohemoglobin, HbCO2. That carries about 25%, 24% of your body's CO2 back. So a lot of it comes back as carbonate. So it's not as highly. Something like 98% of all your oxygen is carried by hemoglobin, only about 25% is carried by CO2. But also, those of you that did sound familiar, which one am I missing?
I forgot.
Do you do reduced hemoglobin? HHB?
What's that for?
Well, at your tissues, it's more acidic. And we need to buffer our tissues. One of the important buffering actions of our body is to get rid of that acid and carry it away. And that way it can sop up some, otherwise your tissues will get more acidic over time. We talk about our body having a buffer. It's really a buffer for acid. Your body's solution to like things becoming too basic is just like, let's slow down on the buffering of the acid, because your body's just always becoming acidic. You are always producing CO2, which binds with water, which makes H+, and so sopping that up and moving it around, and there's a lot of metabolic processes that just make acid. So you're always making acid. What happens to the graph and relative concentrations of all species after an acid is added to the system? We already did that. Take it down. Boom, go. Describe common buffer systems in industrial, environmental, or otherwise. Did I? Oh, I did. Excellent. Biological. So we talked about blood. Blood is buff. Cell function, enzyme activity, metabolism. What happens when things become too acidic or basic to enzymes? They need nature. And what does denature mean?
Break down.
They break down. Proteins, and just to belabor the point, I'll write enzymes. Denature. At different pHs. And another word for denature, if you're not in biology, is just cook. When you cook a steak or you cook some beans, if you cook bread, you are denaturing the protein. And the protein unravels and it no longer works like it was originally intended, and it's easier for you to digest and absorb. Your guts are built for cooking. We have long ago lost our ability to eat raw food unless you have a really handy grocery store in which you can get the perfect food all the time. But, quote unquote, in nature, our guts are not made for that. It takes a really robust gut system. The other great apes have it. We lost it because we started cooking our food. It made it easier to absorb. So we can spend less energy absorbing and digesting food and more energy thinking.
What if we gave great apes more cooked food? Would they also do the same thing?
Grade 8s?
Apes. Like
Yeah, oh no. Animals love cooked food. It does take less energy to absorb if you have, but it's not like they would become better right away. The first use of cooking the food, what's the immediate advantage of cooking your food?
You get rid of bacteria.
You get rid of bacteria, so you get less sick. And then anybody else that now, say, has a mutation in which they don't have as good a gut, actually ends up having more children. Because their now energy is going to do other things. And so they now get a slight advantage for having, quote unquote, a worse off system. Like you can't digest as many different kinds of foods. But you're taking advantage of the fact that you can just digest your food outside your body. You can cook it. Sophia, can you put away the laptop? Shut it in your back. Industrial fermentation, the greatest thing in the entire world, and would justify this no matter what, cheese. Even people who are lactose intolerant agree everyone has to eat cheese.
How are antibiotics?
How do we make antibiotics?
With antibodies.
No, they bind to it. Are you in anatomy and physiology?
No.
Good. Antibiotics, well, they don't all bind. Antibiotics, anti meaning against, and biotic meaning life. So the word literally means anti-life. They're a chemical that kills bacteria. So if your bacteria has a wall around it, like a plant, cell wall, penicillin punches holes in the wall. And since our cells don't have walls, it doesn't harm us, mostly. And that way it is like a bit of a silver bullet. It only kills those bacteria and you get better. But they're made by other bacteria. Bacteria, yeast, because bacteria have been fighting bacteria and yeast has been fighting bacteria. Everybody knows the story of how penicillin was invented?
Yeah.
Bread
No.
mold. And bread mold, they found out bread mold spores contaminated the petri dishes of a microbiologist, and he noticed that it was killing his bacteria around the spores that were growing. And he was like, instead of throwing the plates out, because now his experiment was ruined, he went, why is it killing them? And extracted the first penicillin from bread mold, a type of bread mold. Now we grow it in giant vats of bread mold. We now have fermentation, antibiotics, cheeses, mining. GMO. Yeast. Yeast is great for making all sorts of things because it will just grow with food and then just make product that it will swim in. So we can now make insulin. If you know anybody who's diabetic, they are getting pure human insulin. And no longer do we have to go to dead bodies and extract it, what little there is from their pancreas. That's what we used to do if you were very wealthy. If you weren't very wealthy, then you either did without or you extracted it from like dead horses and pigs and just see how well that does. And their extraction processes weren't great. There'd be little bits of, dead cells in there. It was not very good for you. Even the human one wasn't good for you. But as soon as we sequenced it, we put it in yeast and we, told the yeast, make this, and now they make it. In the same way that we would use yeast to make alcohol, we now use it to make insulin. Genetic engineering has now been around for a fair while. We use GMOs to make all sorts of things. Human growth hormone. There's a lot of metabolic diseases in which the fastest and easiest way to make a lot of that is to just give it to another organism and say, go to town. Start making this for us. And delete. The environment, we depend a lot on our lakes and oceans sopping up the pollution we keep insulting it with. The limestone buffering of lakes, is a classic example. A little bit of acid rain, a little bit more limestone dissolves, lake is fine. Unfortunately, acid rain, because it's continuous, pollution absorbs into the atmosphere, nitric and sulfuric acid rains down in the lake, then water evaporates from the lake in the water cycle, and the acid is left behind. And then more acid rain goes into the lake, water cycle, more water evaporates off the acid, and slowly the lakes become more and more acidic because they have burned through all the limestone that was in the buffer. They've run up, and now they're just changing their pH. So once exhausted, we will get damage to the environment. We don't have a buffer anymore, and some lakes in Canada died quite badly. All the fish were lost. It was particularly prevalent in 60s and 70s when the U.S. had manufacturing industry and all the acid rain and no pollution controls. The pollution would come up over Canada, rain down on our wheat fields and rain down on our lakes, and we would get angry about that. But then everybody took their jobs and moved them to countries far away, and so now nobody cares. Yeah. That's how we solved it. Also, if you make a factory, you put pollution controls in now, and that's much less of a problem. But it's also cheaper to just not do that in another country, and they get all the pollution. Slowly, those countries are discovering the same thing. There's now new environmental controls going in all sorts of countries because they find out that their lakes are becoming dead, and the smog in the city is so high that they can't see. This is the chemistry gnome of good luck. I wrote it on an exam, and it saved me on the exam.
Your chemistry gnome saved you?
Yeah, I was chemistry 232, 332. It was on inorganic. It was on catalysis with a focus on inorganic catalysis. 3-question exam worth 80% of my grade. I open up. I look at the first question. I have literally no idea how to do it. Like none. These are words I've never seen before. I studied hard. No idea. Turn over the second page. I recognize some of the words. Still don't know how to do the question. There's only 3 questions on this test. I drew the gnome for inspiration. Didn't do it. But it got me thinking, and when I went to the 3rd question, I also do not know this question. However, enough of the words related. I'm doing a chemistry, biochemistry double major. We have just finished. I've done 2 courses on enzymes. Enzymes are a catalyst. This is a catalyst course focusing on inorganic, but the principles should be the same. So I wrote everything I could think of about enzymes and catalysis and how they work and drew little biological diagrams. And I got 42% in the course, which was an A, so I passed.
Oh, it was it? That's
It's an A.
great.
42% is an A, because in the province of British Columbia, for example, we do this, and it's intended that a teacher writes a test so that the average student will get a C+, and that will be roughly 67%. And A's, here's 86%. Here's all your A's. Here's all your below 50%. And the bulk of it's in there. At university, they don't do that because they have 500 people in a class. They can just have you write the exam and they go, okay, 42% is an A, 23% is the average, and anybody who gets less than 8% fails.
So it just depends on how good people are.
So it just depends on the average. Yes.
Is this the same gnome as the gnome friend who lies to you, or is this a
No,
different gnome?
this is a better gnome. Much,
Okay.
much better.
Do
I'd
they
never
associate?
put those together, so in one sense I have to be maybe. So, chemistry gnome of good luck.
What's this
So you
one's
literally
name?
answered one question.
If the other
and
one's
then-
friend. Friend who's
He
name?
passed.
And then you passed.
And he got a
Yeah.
Didn't even answer.
Well, the
Right.
final exam was 80%.
80%.
Yeah, the labs are with 20%.
The
If
other
you
one-
don't pass the labs, you don't pass the course.
The other one is Fred. Who is this?
I was gonna say go.
I never gave him a name.
Is he just
That's
secretly
just
Fred?
the chemistry gnome of good luck. Now that I say that out loud, this whole thing sounds vaguely suspicious. Who doesn't give you a name?
His name is Knoll.
Gnome.
Chemistry gnome of Yeah, Knoll.
No, gnome. Well, we wouldn't pronounce the G though, because we don't pronounce the G in gnome, so it'd be spelled with a G.
Knoll.
So,
But Knoll is funnier.
so the chemistry gnome of good luck would be
And
CGO L, so it would be coal. Because you don't pronounce the G's.
Can I, if I draw this on my test, can I get extra marks?
Yeah, can I get a bonus mark if I replicate your
Well, a key part is that I actually ended up
I
writing
think
something in marks.
Kagoggle is
I got
funnier.
0 marks for the gnome.
What if he pronounces G's, he's Kagoggle? He could be cool or Kagoggle, and one of those is better.
What was the first one?
Kagoggle.
I like Kagoggle.
If you do pronounce the G's, he's Kagoggle.
Okay, everybody come up here. Yes. Who said no? Let's go.
Right? Kagoggle.
I can switch you back here.
No.
I have an intro.
Cool is not as funny as Kagoggle. I will be
Use the webcam.
No.
Are
Go
those
for
the
it.
ears?
Come on up. There's not that many people in the class.
I need to know
No,
what-
put,
The students who
oh
are
no,
watching
right,
online.
you can.
I need to know if these are ears so that when I replicate them, I know what
Mr.
it is.
James.
Are those
I
ears?
think they're ears,
Why doesn't he have a hat?
because I wouldn't draw horns.
Oh, okay.
Yeah.
So, where's his hat?
I was quite proud of the fact they used double lines for the torso, so it didn't look like he was just a pencil sketch. That's like artistic flair.
Those fans don't get massages.
Okay, I
Those
have
fans don't get massages.
water and
Yeah.
water. This should be a buffer. Now, if I added acid and base of these right now, nothing would happen because there's no universal indicator in them. So let's do some
Wait, what are you adding?
universal indicator.
But what's it called?
Universal indicator.
It's not like.
No, it doesn't have a fancy name. It's a mixture of things. It's a mixture of indicators. It's the standard universal indicator with the standard colors. So we notice it's a little sort of light yellowy green. So that turns out to be 7. So both of our pH of our water, freshly distilled, turns out to be, we had one that wasn't freshly distilled, and it was actually much more green, and it was like, that's more basic, which didn't make sense. Maybe contaminant, but still worked as part of the demo. So, water, 1 molar hydrochloric acid. I will add a single drop.
Oh, nothing.
I don't know what. Oh! I don't know what's going on
Okay.
right now.
Well,
That's so pretty.
now that's gone to red. So that went from a pH 7 to like 2, like boom, all the way there. Now we take a buffer.
That's my deal with the boil.
Buffer. Single drop.
What's on it? It's my deal.
Nothing gonna happen.
Nothing.
More.
This is the buffer.
Green.
1,
Oh my
2,
God.
3.
It's gonna turn blue.
How do you know?
Why would it turn blue?
I don't know.
It's a
I'm putting my
buffer.
money
1,
on
2, 3,
turning.
4.
Yellow. It's gonna turn yellow.
Still eating your pasta.
No, just
More
wait.
buffer.
What's the buffer?
It is the buffer. You have to
Buffer.
add an
1,
acid.
2,
Oh, buffer.
3, 4, 5.
Boofa.
Is this
Where's
supposed to
Latanya?
be the same
Yeah,
number?
it's
1,
an
2,
orange.
3, 4, 5, 6.
And both.
Has it changed color at all?
No.
No, so this is getting boring.
It hasn't?
Squirt it in.
Oh!
Oh, it's
Whoa.
Yay.
But even then,
fighting. See, it's blue now.
still fighting back. I overwhelmed the buffer by putting a bunch in, but it's still not quite as red as that one. So a buffer can work now. Can a buffer work both ways? 1 molar NaOH in water.
Blue.
That's not blue. That's purple.
Purple. The very, very dark blue one here is very purpley. It's just that it's so dilute. So we have that down there. We take our buffer. Oh, that's HCl. 1, 2, 3, 4, 5. I think that was just 4.
Wait, you added NaOH, not the
We're taking
It's gonna turn blue.
What?
Were you adding NaOH or buffer?
NaOH.
Yeah, blue.
This is buffer.
That is buffer.
Yeah.
What buffer?
In case I get any on myself, because that would burn my hands. Now, is it changed from before?
Yes.
More.
It's a bit green.
It's been green.
Oh.
More. That's not gonna do that. Equal buffer.
Wait,
Oh,
it's
like
turning
light
orange.
blue.
It's not.
It's not turning anything. Just squeeze it all in there.
Literally orange.
I think you're wrong.
That's gonna turn blue. I'm betting my money on blue.
Yes, it's
There we
blue.
go. There we go. I
It's
told you.
purple. It's
Oh.
like slightly
It's
orange.
It's gray.
It's not.
No, it's gray. What?
Sophia.
It's
Now a lot, it only went to blue, not purple. Whereas these ones, very easy.
See, that's
Change.
chemical blue.
Which was
What the hell's
that one? Let's go this one. Now, universal indicator. I want that one.
Are we adding more buffer?
Nope.
You're adding base back in.
I'm adding base back in.
Let's do
So
some
it's
fun
to
light
just-
tests. Oh,
Pure water.
So you can just play around with the equilibrium like that?
Equilibrium goes back and forth. Water, the only equilibrium we have is the water equilibrium. H2O goes to H plus plus OH minus, which has concentrations of 10 to the minus 7. So any amount of acid or base overwhelms that right away. But for these, they take a lot more work because,
Oh, if it's an
so
RCA,
did that one go all the way?
It's no sienna.
Added a few, went back to neutral.
What are we doing right now?
We're adding acid and base to a buffer.
So much is happening at once. And I'm just like,
It's not. It's just
No,
acid and
there's
base.
not that much happening.
I love the
now
color
it's back to
change.
I'm just distracted by the
That
clip.
is
He's
such
trying to
a
add
good
base and it's not
That's-
working. The buffer is already in there.
Still, not, now the other one was able to change back
Because
relatively
like adding,
quickly.
isn't it because like adding basic to an already basic buffer is just gonna.
Well, what we did, we overwhelmed
Well, that was
this
an acidic
buffer
thing.
the other way. But once I added base, it took it back to neutral, and now all the chemicals are there again. And so it's working as a buffer. So if we could, rebuffer our limestone lakes.
acidic or basic?
Hmm?
Would that buffer be acidic or basic?
Oh, I picked a buffer that's a pH of
What is
7.
he adding to them?
Yeah.
So are you adding acids? No, you're adding bases.
I'm adding NaOH, because it went
Oh.
So can we just like pour a bunch of baking soda in the lakes and it'll be like good?
Facts.
Similar types of things have been proposed, only they usually, limestone rocks. Our marble statues, anything made of limestone that we carve, slowly gets dissolved away in acid rain for that reason. If we took a bunch of those rocks and threw them in lakes, yeah, they'd act as part of the buffering system, because they'd absorb the acid. But if we keep adding acid, we're eventually going to dissolve those away, and we're back to the same problem.
We
We
can
have
just
to
keep adding.
We have, well,
It'll be
we're
fine.
gonna run out eventually.
Don't think about that.
Don't, the
That's
environment.
People in the
That's
future will
fine.
figure
People in
something
the-
out.
yeah,
People in
yeah,
the
yeah.
future will figure something
So
out.
I think, should I do this now, or should I do this later? No, future me's a jerk. I'm gonna put it off till later,
What's later, sorry?
It's
or
not.
whatever task I have to do. Just put it off to
What
tomorrow.
happens if you mix them all? Okay, enough. No.
Uh-oh. Whoa! That's
Oh,
10,
Whoa!
You're
No, that's 10
Ten.
minutes.
messing with us.
let's go.
10,
10
10,
push-ups. Okay,
or a lab job.
I'm doing push-ups.
But I could give you a lab
Oh,
job.
do a lab job. That'd be fun.
I had someone write
He asked
down,
you to do that. Okay, your face
You
is
go
purple
deeper.
like Mr. News.
Wait. I'm almost at 10. 8.
Nobody asked you to do my gloves.
yes, it's not that bad.
Mr. Neufeld.
There we go.
Mr. Neufeld.
Hey.
So I added way too much
Anyway.
base.
Mr.
That's
Neufeld.
not very pretty. Oh. Oh, it's yellow again. That's also not pretty. What? What? Where's the pen?
It's fine.
That's the good color. Yay! Success.
Yeah, good enough.
That's a watermelon. I love chemistry when it's boring. It's
Whoa.
not boring.
That's taking quite a lot to do.
I love chemistry. It's pretty and not boring.
Yeah, this is the prettiest.
It doesn't scratch it.
Once you learn about indicators, you realize that every single science show you've ever seen, and they showed a chemist, was just them with a bunch of food coloring, or if they did anything with it and changed color, it was just an indicator. And they were doing absolutely nothing. Okay, you gave me a booklet. Be prepared for the size of this booklet.
you just combine that booklet with this booklet?
Don't ask a silly question.
It's not a silly
Hey, what are your
question.
phone? I'm gonna
It's
take
a lot
it.
of different questions.
Yeah, Teddy. Yeah, Felix.
I wasn't on my phone.
Yes, you were.
You lit us.
That's a calculator.
Thank you. Yeah, because we finished our
Oh,
calculus.
it's literally
That was
1
so-
Mr. Nicole,
Yes?
can I have one of your laptops? Can I
Kill
get-
him.
R.
No.
One single paper.
No, I need them.
Where's S?
You didn't need
All of
You
them.
could, because then you could go shopping for a new one.
It's money. The
Mr.
school is
Nicole,
nice.
you should
The
get
school
Louis
pays for one
Vuitton-
lap.
Louis
like
Vuitton
every 10
laptop.
Okay, you could be like, it's my 10 years.
I already bought a whole bunch. They kind of know.
Should we get him like a?
Okay.
Why is this so
Why don't we get him
small?
a lab coat?
Why not just add just a few? Yeah, no, why not just add just a few?
But
Why
make
do you
it
make
like
all this?
It's just one page.
Yeah.
You
Why?
monster.
Stop complaining.
We should do a test on.
I mean, do you want more pages? Okay. Metal oxides. The outside coating of pure sodium, that little whitish thing that you saw when we took it and threw it in the ocean, it would react right away. If we have calcium oxide, or, well, any of them, even if they're not very soluble, even if this is an equilibrium. So could be two ways, could be one ways. Now for sodium, it's definitely going to be one way. But for calcium oxide, it's going to be an equilibrium.
Wait, why?
But it will give off an A plus plus O minus 2.
And why is that the case?
Why is what the case?
That Na2O,
What's sodium soluble with?
everything. What's the A zone?
Not nearly as much.
Not everything.
Yeah. I think calcium oxide, because I've seen calcium oxide form, it doesn't dissolve all that easily. It makes it precipitate. However, it will have an equilibrium. And the part of the equilibrium that matters is that it's giving off a little bit of oxygen. Well, not oxygen, oxide ion. And if you look at your table, on your acid base table, what does the oxide ion do?
Now it says base only.
Hmm?
Like hydroxide.
Well, there it is. Can you find O minus 2 on here?
Very bottom,
Very bottom on what side?
right side.
Right side. Bottom right side. This is actually a strong base. So most of the time we use a strong base, we're talking about
OH.
OH minus. This is one of the few. This is a strong base. And it makes hydroxide. So if you have any, now this is true for any, you have rust, iron oxide, you have copper oxide on the roof of a building, it will make, now it might make it slowly because this is an equilibrium, but as soon as that comes out and reacts with any water, so it rains, then the solution will be a little basic.
Is that why the
And it will
copper-
just keep going
Is
that
that
way.
why copper roofs turn like things more slow than?
Well, a copper roof will react with oxygen to make copper, which is copper is most likely CuO. I think it's more likely to be +2 or Cu2O. I can't remember which is the really green form that forms. I think it's that one. And once it does that, it performs a relatively protective coat from the rest of the copper reacting. And very slowly over time, it will do this. So the drippings coming off of it will be a little basic. It's relatively insoluble in water. So not much of it comes off, but when a little bit of it does, it's just going to drip away with the water. So very slowly that they will wear away over time. Now for copper, not that quickly. We've used it as a roofing source for a long time. Our parliament buildings are roofed with it, but they do have to be replaced every once in a while. Or if you coat it in plastic, and then it just stays nice and coppery like that hotel in Victoria. So ionic metal oxides form basic solutions. Non-metal oxides. So this is for Knox and SOx.
What does that mean?
Knox and SOx.
What does that mean?
Knox and SOx.
Well, what does it mean though?
I just wrote it. What does the X mean?
Any number.
Any number. So these will make a variety of things. NO, NO2, not NO3, but N2O6, SO2, SO3. I don't think there's any sulfur oxide, etc. There's a variety of these. It's made in the combustion of petroleum products. Not metal. We'll add another one. CO2 is also produced in this. We don't, and we also have carbon monoxide is produced in this. If you don't have your garage door open and you turn on your car and you just let it produce the gas that's going to kill you is the carbon monoxide. So these are all produced in the combustion process. Nitrogen is just in our atmosphere. It is stable. We don't do anything with it when we breathe. We breathe it in, we breathe it out. Plants and some bacteria will grab a hold of it and use it to make nitrates for fertilizer. And we figured out how to do that in the Haber process that we did earlier in the year. But most of the time it's a relatively stable gas. But if you put it in a combustion engine at high temperature and pressure, which is what it's doing in order to burn the gasoline, you'll get these as a byproduct. And sulfur is present in fuel as an impurity. So there's sulfur in your fuel. Pardon?
Petroleum products?
Gas.
No, I just mean, is that what it says?
Yeah, petroleum products. So let's take a couple. Take a guess. If I have NO2, and that goes up and mixes with clouds, what will that make? What's a product you know exists? Pardon?
H.
OH minus.
I know, no, N2O6.
Nope. There's hydrogen and oxygen in there. We had hydrogen and oxygen for that. What will we get?
Hydroxide.
Pardon?
Hydroxide.
Where you left out the nitrogen.
NO.
Nitrogen hydroxide.
Pardon?
H2O.
Close.
NOH.
Close. It wouldn't be H2NO3, but HNO3. You'd have to balance for the other H. Oops.
Why
HNO3.
HNO3?
That's the product of that particular reaction.
You can't make HNO3
Why can't you?
because it's strong acid.
Yeah. Why can't you make it if it's a strong acid? We didn't make it from base. We made it from the gases. So now we've made nitric acid in our atmosphere. It's now going to come down in our rain.
Well, why can't it be HNO2?
Oh, it can. If we have NO plus H2O, does that one NO2? Yeah, what does that one make?
HNO has OH minus.
HNO2.
Why HNO2?
Because there's two oxygens.
There's two oxygens there. The hydrogens you'll solve by balancing, but that's what it makes.
Why is it not like the acid and base reactions that we did earlier?
These aren't acid-base reactions.
Oh,
Because there's no acid and base. This
I
is
mean,
just
H2O is amphiprotic, so.
yeah, but H2O can also be a catalyst. It can also be part of an acid-base reaction. It can also be part of a reduction. There's all sorts of reactions that water can be a part of. It's not an acid-base reaction. There's no H plus. There's no H minus. It is just making acid
So what's H2O doing right now?
in that reaction,
Yeah.
reacting with nitrogen oxides
So
and making acids.
Is it a catalyst? Is it a
No, it
acid?
what is a catalyst?
Speeds up a reaction.
Right,
Doesn't. Like,
but it doesn't take part.
take part.
Did it take part?
Yeah.
Yeah, it's just a reactant. We can do this with more of them.
Who told H2O to react that way?
It just does. If we have SO3 plus H2O, guess what we get?
HSO3 plus OH minus.
Nope.
No. HSO4.
Close.
Wait.
What H's go with SO4? How many?
H2.
H2SO4.
Wait, but then why do you drop the H on the other two up top?
Because nitrogen, nitrate, nitrite, and nitrate are both -1. They only can fit one H. SO4, which you just made, is -2.
Oh.
And so it's fitting the amount that you could fit in there. If you have CO2, as I've mentioned before, and you have water, what does it make?
Would it make carbon plus base? No.
H2CO2.
H2CO3. Carbonic acid, sulfuric acid, nitric acid, nitric acid, nitrite acid, hold it, nitrous, that's the word I'm looking for, nitrous acid, nitric acid. So if you take any oxide of a covalent compound and react it with water, you form an acidic solution.
Where does the other hydrogen go?
You just balance.
Is
Just
it a
balance the equation.
Synthesis
Right?
reaction.
Yep, there's synthesis reactions. So when you react something, like when you go, I went sodium plus chlorine gas, what would it make?
And it's
NaCl.
NaCl. Where'd the other chlorine go?
directed with an extra Na.
Yeah. Pardon?
To balance.
A so you balance it.
But how do you balance like the first reaction?
Well, I'd have to get in there and balance it.
Yo, where?
So I've got 3 on this side, 3 on that side, so that's fine. I've got 1 hydrogen there, so I'm going to need, and 1 nitrogen. So I'm going to need 2 of those. Oh, right. No, no, no. These are also, the hydrogen's going from, the NO's going from NO to NO2 minus. These are also an example of redox reactions. In many cases that occur in the atmosphere, we are going to learn how to balance redox reactions later. Because you can't balance them the same way you balance other reactions.
That's very confusing with the new power.
Well, that's why we'll
Wait,
learn
so
how
these
to
are
balance.
redox reactions
These are redox reactions in some cases.
That's why they
because
don't balance.
why?
Um,
You should balance
If
those.
they are redox reactions, I think a couple of those are changing their charge. If they're not changing their charge, they wouldn't be a redox reaction. Some of them are, some of them I think are not. It's the CO2 and that one's not a redox reaction. That one I think is. But yeah, you just balance.
But it's not balanced.
Yeah, that's okay. It's just an example. We don't have to balance it right now.
How do we know that, like, during the assessment,
What?
how do we know that it's, like, not, it's fine to be not balanced during an assessment?
Because if the assessment is, if it asks you what the reactions are, it didn't ask you to balance it.
Yeah, it could be a student knowledge, though, like, balance.
It could be. You're right. Being a student is hard, which is why. Here. We're going back to the gnome. Just look at the gnome for a moment. Feel calm.
Will you tell us whether or not we should balance?
For this particular learning outcome, I just want you to know that if you have non-metal oxides, they will make acidic products. And the acidic products they make, you can guess. You just look on your table and goes, what has hydrogen and those things in it? And if you guess wrong, I'm not going to be too worried. If you told me that NO made NO3, I'd be like, okay.
What do you mean, okay, you're still gonna
Sure.
deduct that one mark?
Because I don't need you to memorize what it makes. I need you to know that it's acidic. It's grade 12. You're not in first year chem yet.
Yeah, but if you mark that this is a PLOR question, then no.
Yeah.
Are you going to do that?
Oh, when I make the test, yes. I'll know which one is which.
Wait,
You might not.
well, we need to know that too, and so.
Wait, so we need to memorize all that?
All the acids? No, you get your table. No, Eric was asking, I think, if he could get, know which question does which section,
Yeah.
and we don't do that. However, I put them in order. It starts at A, ends at the last one, and then just... So you can take a reasonable guess.
I don't need to know. I can definitely figure out whether this is like a K-A or a more recent K-value.
Yeah.
Fine.
Now, CO2 reacts with water, as I've said before, to make H2CO3. H2CO3 itself has an equilibrium called H plus CO3 minus. And in fact, this occurs so quickly that there are chemists that don't believe H2CO3 actually exists. I've heard arguments. We are going to accept that it does.
Why do you believe that it doesn't?
It's one of those, it doesn't matter. Because it's either in this form, and then it goes through that form and gets to there. Or it's in this form, and it goes through that form and gets to there, and these are the only ones you ever really worry about. So practically, any work I've ever done, it hasn't mattered.
Why is there like two? What the hell? There's two like arrow sections. H.
Yes, there's 3.
What? Yeah.
It's like a million reactions in one.
Those, it's 2 reactions, centered around this as a reaction. So
What kind of reaction is
this would be a synthesis going that way, and then H2CO3 would be an acid reaction, which would give you an off H plus.
How come we've never seen this? I've never seen it.
Because I don't know.
What?
I just did it.
Okay.
I didn't expect this to be the amazing part. But reactions can keep going. Whoa, wait till you see biochemistry. The Krebs cycle is just this in a circle with reaction
Is
after
that a
reaction
hard
after
class
reaction after reaction.
biochemistry?
Pardon?
Is that a hard degree of biochemistry?
Yes.
Yes.
It's considered to be one of the more challenging ones. It has all the chemistry of chemistry and all the memorization of biology.
That's messed up.
No, I liked it. Because you fundamentally learn about how your body works. Everything else is just nonsense. Okay. I don't know if anybody can look up in the last 20 years. I don't know what the most acidic rainfall has been lately. I updated 2000 last time I checked. If you get a pH of less than 5.6, that's called acid rain. Because the amount that will make it to is 5.6. So we would expect a pH of 5.6 at the lowest if we just had, the environment. Most acidic rain in the U.S., pH 4.3. I'm using the U.S. because that's the only place I can get good data on. Apparently Canadians don't know what happens in our wilderness. where is most acidic rainfall in North America? Fraser Institute. Oh God. This is an old book. Go away.
I think you're distracted.
They're talking about sulfuric acid now, which I just mentioned to you. I can't find a better value than that one. From 1978 to 1979, they had, and I can't, this, Canada apparently had 4.0.
At what point does it start to like bother your skin?
4.0, if you were in it for a long time, would start to bother your skin, but you might mistake it for the fact that you were just wet for a long time. It's not great at that point. You eat, however, lower than, like a lemon can be 3. But if it was literally raining lemons, like that would kill most fish and wildlife over time if it built up. You can withstand it because you are built to take a little bit of acid when you eat food. And your skin is mostly repellent, so for a short term. But if you, like, for example, vomit on the carpet, that'll burn your carpet and leach out all the colors because your vomit has a pH of like 2.
Wait, so if it was raining
Can
pH
it like
of 2,
burn
you
your
would just
esophagus?
you'd be like done.
It would no, it's not like instant, but yeah, you'd start getting chemical burns. Yeah,
Can like your throat like burn your esophagus?
yeah, that's why it hurts.
That's what I'm having right
You're
now.
burning the flesh of your esophagus as you throw up.
And it, then as you throw up a lot, like, is that when you get hospitalized because it's like just destroys your esophagus?
Yeah, it destroys your esophagus. The epiglottis that covers your esophagus can be worn away, such that when you lie down, now your stomach acid will just flow through it and burns it constantly. That could be a very serious health condition because you can actually burn through your esophagus and now have acid leaking into the rest of your body. Like a bit of well, that's an ulcer. Oh, last one. Describe sources of NOx in socks. Fuel. Coal and oil contain sulfur. Combustion reactions convert them into the NOx in socks. So. Product of combustion into an atmosphere and the most common way to get this is N2 plus O2 goes to N2O6. And N2O6 goes to NO3 plus NO2 plus N2O5 plus NO plus, I'll just do dot 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 at that point. 2 arrows. Two arrows. And actually this process itself can make those, but it often goes through this as a pathway. And it just makes all of these nitrogen oxide products. There are just a ton of these that are spewing out. This is why cars should have filters. One of the main pushes for electric cars wasn't just the CO2, but to reduce the amount of toxic gases that were released into our atmosphere. Even if you burn coal to make power, and then you charge your electric car, you are producing less gas in that process than if you just burn the fuel in your car. And the reason for that is burning coal at a power plant can be very efficient. You'll get a lot of electricity out of that energy change. But when you burn gas, it's about 30% efficiency. A lot of it's wasted, a lot of it goes into making this stuff, a lot of it goes into noise. and it's not very efficient. And so you're using it directly, but you're using it in a very efficient way. If you burn it efficiently and then pipe the electricity to the car and then charge the car, that reduces the amount of gases.
Well, what like
But the lithium and cobalt from the batteries, that's really bad for the air.
The lithium and cobalt are particulates that will drop out of the air. It's the nitrogen and the carbon, nitrogen, and sulfur oxides that'll stay in the air. The cobalt and lithium, I mean, everything's got products. You should recycle your batteries. But we're not worried about them in
It's
the
a
air.
mining process.
The mining process, yeah,
It's like really bad.
yeah. So is oil and gas. I mean, ideally, we should have nuclear power plants. But in the meantime, if we're burning coal to make electricity, we're doing a better job, and then convert that to a nuclear power plant. All of the nuclear waste in the world that we produce in our nuclear power plants could probably fit in a building smaller than this one. It produces very little waste. We produce more nuclear waste burning coal than we produce in our nuclear power plants. Except that just gets thrown into our atmosphere and it's widely dispersed, so we don't worry about it as much. But there's nuclear products in coal itself, and then we burn it.
We know
what's
this.
the catalyst that mitigates like
Pardon?
what's the catalyst inside like
Oh, yeah, the platinum catalysts and stuff. They're catalysts that will do something like this. They'll take this NO2, and a platinum catalyst will turn it back into that.
and that makes it less poisonous or
Yeah, because now you've taken it away. It doesn't work perfectly, but it works reasonably well. It does cost a little bit more energy for your car, but not much. I mean, people who are like weirdly concerned about mileage will like remove it and just pollute the environment more, and it's like it's not that good. I mean, not that wasteful. But yeah, yes.
Do they not use as many nuclear power plants because of what happened at Chernobyl?
That was a really badly designed Russian power plant, but I think people are more scared of radioactivity than they're scared of other things.
Yeah.
Which
Like-
is, stupid.
are there any
You've
formula
has anybody here had an MRI before?
race car?
Excellent. MRIs are not MRIs. They're NMRs. It's called nuclear magnetic resonance, and that name makes sense.
What's the first name?
This is magnetic resonance imaging. They got rid of the word nuclear. There is something specific about the nucleus of some atoms, carbon-13. They're not radioactive, but there is a uniqueness to their spin. And you can use that in magnets to then take a picture. And for commercial machines, they found no one would get an NMR unless they named it an MRI because people were just scared of the word nuclear. So if you go to university, you do chemistry, you'll take your molecules and you'll do an NMR on them. It is the exact same machine, except much smaller because molecules are tiny. So instead of having a giant MRI, you have a little box. And it does the NMR right in there. So yeah, people are just scared of the CANDU reaction. The reactor that Canada has is an incredibly safe reactor. The US has a few good models.
X-rays are radiation too.
Yeah,
Are people more scared because of what happened in Japan?
No, mainly
I mean, in terms of risk, even the Japanese disaster killed less people than their combustion process produces in 5 years. There is still not a single attributable direct death to radiation. Most of it's due to accidents, like people trying to respond to the emergency. It was a safe reactor, and even when it was hit by a tsunami, did not release much. All reactors might have accidents eventually. You don't want to build one on a fault line, but you can have them shut down in a safe way. The Russian one, does anybody know the story about how?
Yeah, it
Yeah.
just the way that it was built, like when you hit the kill switch and
Yeah.
stuff, it just basically continues it.
It continues it. And there was no reason to hit the kill switch. They were like, let's test the kill switch.
Yeah.
And everything went wrong.
They made a really good show out of it.
Yeah. They made it really good. The Canadian one, if anything goes wrong, if it falls apart in a way that takes all the pieces away, and so it won't continue.
They tested it.
They had to kill switch, and instead of reducing the amount of radiation, things fell in a way that increased the reactor.
They just hear.
Because they wanted to test if it would work. They were like, we should do a shutdown and see what's going to happen.
Yeah.
But like they didn't know for like a
Yeah.
while. So like everyone died, like everybody, and then like the whole town got like radiation.
Yeah, I know what happened after. I just didn't.
We don't actually know if that's the only one. There's still a conspiracy theory, and we're not allowed to go there because it's near where Chernobyl was. But there's a town based in the Cold War. You'd look at maps and like all the towns, and then Russia's maps just eliminated a town. The town's gone, and we were pretty sure, as in like U.S. and Canada, Cold War, that there was a nuclear reactor, or at least a nuclear reactor test site there, and it's just not there anymore. We don't really know what happened. We didn't detect a lot of radiation at the time, so it might have been a test site, but the town left. This is required reading.
Is that it?
Yeah, you're done for
Okay.
this.
Are we doing another thing today, or?
Wow, now.
Oh my god. I had 3 PLOs in one day.
Wow, we're so bad.
Aren't you lucky?
Is it lucky?
This is so lucky.
You draw the no and go to your dreams. I draw the no. I'm sorry.
What are like the question types for PLOR?
Wait,
Oh,
Right away.
what is the pH of acid
did
rain?
anatomy test today?
It's like just memorize.
Well, yeah, you
But I have like a
can-
different thing for anatomy. You're allergic, I might like that.
Oh, wait, is it all?
Here's a bunch of chemical compounds, which are those introduced in acidic solution. And you go, oh, one of those is a
Like I know
non-metal oxide.
NOx or
Oh,
So
SOx.
I've done everything else.
Well, though, still pretty good.
Or one of them, which one of these produces a basic solution? And then you go, oh, one of those is a metal oxide.
What about the COs?
You what?
The CO2?
That's a non-metal oxide.
That's gonna make acid.
Yeah.
Mr. Newfeld,
Yo, what up, my homie G?
how come you don't work in like the radiation business? I mean, the
How come I don't have the right degree.
What about the nuclear business?
I don't have the right degree. Whoa. I worked at Triumph, the Tri-University Meson facility at the University of British Columbia, and I made radioactive drugs that we injected into people.
Really?
Yeah.
Did you try yourself?
I volunteered.
Is it drugs?
However, by the time I volunteered, there were 6 weeks of workup they'd have to do to inject the radioactive sugar into my body, and I only had 4 weeks left of my work term, so they wouldn't do that.
What did
We use it for positron emission tomography. A report I wrote afterwards won an award at the University of Victoria, and I got a free book.
Damn.
Yeah.
What
yeah.
book?
I have no idea. I can't find it anymore. I don't remember which one it was. It has a little certificate in it that they pasted, so I no longer have the evidence, so you cannot believe me. But I would take a sugar molecule, we'd pop off a hydroxide, and pop on a radioactive fluorine. Radioactive fluorine has a half-life of about 20 minutes, and then you inject that into someone, and you put their head in a positron emission tomography. Now, an MRI gives you a picture, but a radioactive sugar is constantly sending out rays, and if you have a detector around it, you are seeing in real time where that radiation is coming from. So if you are, say, thinking about math, the area of your brain that's used for math on the monitor will just light up because that's where you're using the most glucose. And then if you start like remembering your past, it'll go to those areas. If you move your hand, it'll use the areas of the brain will light up that you use to focus on motor control. So you can see all sorts of stuff. They were trying to cure Alzheimer's and Parkinson's.
That's pretty cool.
Get closer.
Well, they were feeding, they were implanting a little, it looked like a pill, but it was filled with stem cells. And because what you would see is that someone in an area, if they had Parkinson's, there was an area of the brain that was black. It never used glucose. It was essentially dead, and those cells weren't working anymore. So they were going to put stem cells in there and encourage them to take over that function and start producing those signals that are needed for Alzheimer's and Parkinson's. They used monkeys who had Parkinson's.
Monkeys can have Parkinson's?
They gave the monkeys Parkinson's. In the 70s, New York had a rash of drug addicts who would show up to a hospital with advanced Parkinson's. It turns out the drug, whatever supplier was making it artificially, and they weren't Walter White, that's for sure, because they actually didn't make the drug, they made a related poison that it turns out will kill that area of your brain and give you Parkinson's. So now they found a way to make Parkinson's. And then they gave the monkeys Parkinson's. And then they tried to cure the Parkinson's.
What happened to the monkeys when they were forgetting everything?
No. Once they try to cure it, they know whether or not it works because they take the brain of the monkey and they make sections and examine it closely underneath a microscope.
Did it work? No.
No, well, I was there. They were in like the middle of 10 years trials of trying to make this work. So
Well, it hasn't worked now, so.
it's not working now. Stem cells were a hope. They had to go through a ton of ethical review boards to be able to use. You can't just go out and grab a monkey and start doing experiments. So they had started with mice, and it was showing promise at the time. But yeah, clearly we hadn't cured it yet.
You can't go grab monkeys. They grab mice.
Where'd they get the monkeys?
Well, monkeys are a little easier to justify because most people hate them because they're rodents that eat our food.
Mice are easier to justify, not monkeys.
Not monkeys, yeah.
You
Monkeys.
said monkeys are easier.
No. Monkeys are not. Nobody wants. No. The more intelligent a creature, the more work you have to do to justify it, including humans. Like human trials take a lot to ensure. Part of the reasons you can do human trials is because you've shown it hasn't been deadly to some related species. Okay, oxidation reduction. Yeah, baby. Where is? Oh. I don't have the other version of that up yet. Let's go. Okay. Oxidation reduction is all about electron transfer. And this is going to involve a type of reaction that you haven't really seen before, because we've never before put electrons really into reactions. But now we are going to exclusively, or really obviously, do so. And the terminology Dylan's hit one desk over.
What? What did I do?
You're giggling really loudly.
Oh my god.
Oh.
Okay.
Right under the line.
Pull one over. We use it everywhere. You just saw the production of some gases. The process by which nitrogen is taken plus oxygen, it goes to NO3. This is a redox reaction. A redox reaction is called redox, reduction and oxidation, based on terms used by like metallurgists, and the fact that the first redox we ever thought was redox just involved oxygen. We didn't use any other chemical other than oxygen. Since then we've changed the definitions but kept the terms. So the definitions for this are going to be very important to keep straight. Write them down, put them on cards. Don't mix them up, because an oxidizing agent is itself reduced and a reducing agent is itself oxidized. And there'll be lots of terminology like that, and you want to be very clear what it is you're talking about. So, first bit is metallurgists were the first to use the term reduction. And all it meant is that we got a lot of ore. So, for example, Fe2O3. And we would react that with something. So the first smelters would burn wood under very low oxygen conditions. So instead of producing CO2, they'd produce carbon monoxide. And they would funnel that through the really hot ore. That would pick up the extra oxygen, so it becomes CO2, and make iron solid. So this is how we smelted iron and copper and aluminum. Well, not aluminum for a while. It took us a long time to figure out how to do aluminum. We needed really high temperatures for that. But copper was fairly easy to do this too. Iron was a little harder, hence copper age, iron age. It has to do with how hot you have to get it and how easy that process is to do. One of the reasons you will hear stories about the first, the really good metal iron swords were made from asteroids or meteors, is because the iron in those didn't have as much oxygen, and so it was like pre-smelted to a level that the current technology at the time was able to do. And so they made harder swords and better metal. Nowadays, of course, we can exceed that. So in this process, we have a big chunk of ore. Big chungus.
What?
Of ore!
Why don't you just throw that out there?
Big chungus.
Okay, continue.
What is with this class? Small chungus? That was so out of nowhere. Big chunk ore.
Big chunk.
Ore or O-R-E?
O-R-E.
Those are two different things.
Ore. And then you get a small amount of metal. So this was reduced. I don't know what the opposite of big chungus is, but it would go from big chungus to tiny number.
No, you don't.
Punctuate it.
Pronunciation. What is the opposite of a big chungus?
Small chungus.
Well, no, because chungus itself kind of means big. It's chungus.
Chungai.
A little chungus.
Oh no. Chungy.
Yeah. That's so
Chungy?
What is class then?
What are we on?
It's 9:30.
Okay.
9:35.
Small chungy.
No.
No? That's what you said.
Wait, can you write big chungus by the big ones? Just like it makes more sense to my brain. So I'm really not getting it. There's like small chungus there. That gives nothing.
There you go.
Thank you.
Now, what happened here? What is the charge in that iron?
2 plus.
Just iron by itself, plus what?
Plus 3.
Plus 0. Iron, just as a metal, has no charge. But what is the charge on iron here?
Plus 3.
Plus 3. So it went from plus 3 to 0. What happened in terms of electrons?
3 of them came. 3.
Plus 3 of the plus 3 electrons.
Wait, the other side's 0 or 0.
So when you have a reduction, you are adding electrons.
Because electrons add negative.
Yeah. So add 3 electrons. This is a reduction. Because the reduction has to do with the size of the ore. You have big ore and then you have small amounts of matter. You're also reducing the amount of oxygen on it. So the oxygen is being reduced. But when we talk about electrons, all of a sudden it goes from plus 3 to 0. We're adding electrons. What is happening to the amount of oxygen in the carbon to the carbon dioxide? Double. So this is an oxidation. What is the charge on, if this carbon was to have a charge, what charge would it be? I know it's covalent, but knowing the charge on oxygen, what would that charge be if it had one?
2.
Yes? 4. This one would be plus 4. We got oxygen minus 2, and we have 2 of them.
Overall,
Yeah. What would this one be?
2.
Oxygen there is plus 2. So what happened to the electrons from there to there?
There was more.
Did we add, if we went from +2 to +4, lost 2 electrons. Lost 2 electrons. So an oxidation is a loss of electrons. Okay? There are ways that you can memorize this. I learned Leo and Gur. Leo the lion goes Gur. Loss of electrons is oxidation, gain of electrons is reduction. Your textbook and Mr. Snow likes oil rig.
Oh yeah, oil rig.
That's way more like.
Oxidation is loss, reduction is gain. I don't like it because I was confused in chemistry 12. And when it says oxidation is lost, my brain is loss of what? Electrons.
Oh.
Also, I like Leo the lion, so there you go. So a little bit, tiny bit more. This is being reduced, right? Iron oxide is being reduced, which means that this chemical right there is helping it being reduced. It might even be called an agent of reduction. So this is a reducing agent. Don't pack up. You need this. So the reducing agent is itself oxidized because it's helping the other one be reduced, which means this one would be called the oxidizing agent. So the because it's helping the other one be oxidized, it is called the oxidizing agent. The oxidizing agent itself is reduced. It'd be the equivalent if we called the acid in an acid-base reaction the base agent.
It's so confusing.
Yeah. But remember, these terms were not made by chemists doing these reactions. These terms were made by, I have a chunk of ore. What do I need to do to it? I add a reducing agent to make its size go down. They were named before we knew what the chemistry was. Yeah.
Maybe you just change the name.
Yeah, well, physics should first learn that electrons are negative.
Electrons are negative.
No. Have you taken physics? And done standard current? They pretend the electrons are positive, and they refuse to give it up because we have to memorize different hand rules.
Yeah.
You failed.
Memorize it. Memorize it.
So just change it, and then
No, but it takes so long. Like it's so much more words.
if we changed it, you would know the old ones, but next year's 11s going into 12, we'll just learn the new ones, and it would be done.
That's fine. They can relearn.
It's just read off.
That's how bad physics are at science. They refuse to change after hundreds
Go up
of
to Miss
years.
Lawrence and tell her she's bad at science.
She is bad at science. Physics is the easiest science.
Go up to her and tell her that.
Should I?
You describe the trajectory,
Go up to her right now and say
and the
that to her
chemicals
face.
aren't even changing in the air.
Should I repeat this conversation?
No, Miss
Lawrence
Lawrence
will
scares me
have
just
your
a
head.
little bit.
Yeah, should I
I've got
repeat this
quite a bit.
conversation?
No. I will throw people on the bus. I'll say that Taylor did it.
No, I'll say Taylor would never do that.
Eshwan, where are we going right now?
Ashwan, come on.
We're going to
Yeah, they're probably
cook, or Art split that, and then
Nope.
I'll come into the house.
Okay, excellent.
We're taking your couch.
Oh, excellent.
Oh, this is gonna be not fun.
It is not going to be fun to move.
Oh my god. Wait, does it have rollies? Are they broken?
No, there's no rollies. There's those underneath. That broke off.
Oh,
You can see it doesn't even have the thing in it. Also, you don't want to scrape it along the carpet because there might be a piece of metal poking out, so that'll like rip things. So you actually have to literally carry it.
Oh, no.